What will be the future direction of crystallography, which now is influenced by AI, ML, and also all these great instrumentation developments?
Well, this is a really good question, and I always call it the elephant in the room, really, because from two directions, AI and, well, of course, the AI is really behind the AlphaFold 2 models. The thing is, you still need the experimental data. So the AI models are all based on the data from the protein data bank. Without that, all those experimental structures, it wouldn't have been possible to predict the structures of another 3 million proteins. And the argument for crystallographers is that crystallography isn't dead and you still need to actually determine these structures. But what we haven't mentioned is the huge improvement in resolution available from electron microscopy now. And for small proteins, you still need to do the crystallography, but electron microscopy has really taken off. However, a lot of places have bought electron microscopes and are not seeing the results they would like from them simply because the sample preparation is still quite tricky. And you need people who really know what they're doing to get the best results. And I think that's an upcoming, education run that is required and will happen. We've got a paper that we're hoping to submit actually in about 2 weeks, where we've measured another 70 metalloprotein, the content of them using the microPIXE, the proton-induced X-ray emission technique I mentioned earlier. We'd already done a high throughput. I had a student who worked on making that high throughput technique of printing using a non-array jet printer. A non-contact. The company is called Radar, using a non-contact printer to spray 60 micron spots of proteins, 100 different proteins in a 10 by 10 array, 200 microns apart, which we could then scan the proton beam, steer it magnetically and collect data overnight on these proton dried spots. And what we discovered from those initial 32 high throughput work was that a third of them had the wrong metal in their model in the protein data bank. The worry about this is that many, like 1,000 times more people use those data thinking they're correct than actually produce them. So people who know about the models know that the metal might not be right, but people who use them think, well, this is the truth. So we've just done another 70 and discovered the same proportion. About a third of them have the wrong metal in, and they all have suspicious electron density differences when you download the data and the model, showing that the model is probably not correct for the metals. So this is not only have you got radiation damaged models in the protein data bank, which is a whole nother subject, but you've also got the wrong metals for the metalloproteins in many of them. So I'm still a bit active doing those experiments.
Okay.